So, let's continue on with this equilibrium, just finishing it off. Organic, like I said, quite a bit shorter. So this will take, I think, about 15 minutes or so to finish up this. And then we'll get into the organic. Jane, I'll get you a book for the equilibrium stuff. And there's an amazing video from way back there. So I think actually you can't see the board from the last video, but it's up and you can hear the text.
Is it audio then?
I don't know. I listened to it. You tell me. You tell me. I don't even actually know if this is connected right now. Okay. So last question is question 4. What is the pH of this solution? It's the nitrite being 0.400 moles per liter. Now, here's the beauty of this. You just calculated Kb for nitrites in question number 3. So question number 4 should be quite simple. Try this one out because I think this is where people will have a really hard time. And this is typical difficulty again for the diploma. It's kind of a question. Oh, so it's Kb. Sorry, repeat that?
1.8 pound.
Now, also a reminder that you got to memorize these formulas, right? You're not going to have them. You need to memorize those. If you memorize one for the Ka or the Kb, then you're good. Okay. So Kb is equal to hydroxide squared over A minus, which is just our symbol for a generic base. And this is following the idea of a Bronsted-Lowry acid or base, right? It essentially is a proton acceptor. Okay, so finding pH is not a simple thing because actually I have to first go to hydroxide, given that it's a base. Okay, so I have to find the hydroxide concentration first, and then I can take that to POH, that's how I would do it, and then finally to pH. So you're going through a few steps here. So what I would say is OH minus is equal to square root of Kb multiplied by A minus. So I have the square root of that 1.8 times 10 to the negative 11 multiplied by the 0.400. And that will give me a hydroxide concentration. Which is 2.68 times 10 to the negative 6. So we actually have a pretty weak base here, right? That's not a high value. So now if I take the POH of this, and I'm kind of doing some extra sig digs here just to make sure I don't mess up the value. I get 5.57. I have 3 sig digs, so 5.571. But I want pH, so how do I get pH from that? Yeah. I get 8.429. So here's where students fall down on this type of question, is they have a hard time realizing that they can't go directly to pH by finding like hydronium. So what a lot of people do is they go, oh, nitride ion, I'll just use nitrous acid, use that Ka to find hydronium and go from there. You can't do that because nitride ion is not the same as nitrous acid. So this is a base. Nitrous acid is an acid, right? So you have to use the Kb to hydroxide, to POH, to pH. So for a base, you always have to use Kb. For an acid, you always have to use Ka if it's weak. Good for that? Yeah, okay. These terms are just ones you need to be familiar with. So monoprotic, mono meaning one, protic meaning proton. So only one hydrogen to give, okay, for the acid. So only one acidic H. I actually can talk about this for a base as well, which means it can only accept one H. But an example of that, hey, let's use kind of what we were talking about already with nitrous acid, HNO2 aqueous. That would be monoprotic. I only have one acidic hydrogen. Compare that to something that's diprotic, where I have two. Two acidic H's. So like H2SO3 would be a great example of that. I have two protons that can be given. Another one is something like HOOCCOOH aqueous. That is diprotic as well because that beginning hydrogen is acidic, and then the end hydrogen is also acidic, right? That COOH ending you're now familiar with as a carboxylic acid. Oxalic acid is something that can be used in a polyester reaction because it has a carboxyl group on both ends. Polyprotic just means more than one. So more than one acidic H's. So diprotic and polyprotic actually have overlap, right? But then poly goes to things like 3. So citric acid would be an example from your data booklet. Phosphoric acid is iffy on that, even though it's a typically used example. Because if you remember, phosphoric acid doesn't go through its last step. Would the diploma ever test on that? Oh, it would be such a jerk thing to do, but it's possible. They bring it up a lot. But phosphoric acid specifically, I think it's on the next page, does not go through the last step enough for it to matter. Antiprotic was on the information bulletin as something to focus on. So again, antiprotic things can act as an acid or a base, so it can donate or accept a proton. So the classic thing that you should definitely know is antiprotic is something like water, right? Water can accept a proton to become hydronium, or it can donate one to become hydroxide. Other things are stuff like HCO3 minus, where I have both a proton that can be given, and it can also accept a proton as well. It can be both. Describe the following. Ooh, H2PO4 minus. If you were to describe that, what would you say? Can it be an acid? Yes, it has acidic hydrogen. It's going to be a base? Yay! Sure. It can accept as well. It can act as well. Depending on what it's with, right? What it's reacting with. Is it a diprotic acid?
Yes.
Yeah. Monoprotic base. It's weak. Amphiprotic. These are all terms that work. Anyways, hopefully that makes sense. If you're iffy on the terminology, if that stuff to you is kind of like, ooh, I don't feel great about this. Take a look in notes, read through that section of your textbook and just kind of see it can be a little bit confusing. There's a possibility that something like that appears in the diploma of just terminology type questions. Okay, titration curves. We went through this pretty quick in class, and I feel like for some of you it may have caused or could cause some confusion. So when you have a diprotic thing that's an acid or a base, you're going to see more than one endpoint or equivalence point. Okay? The equivalence point is kind of like the most vertical points. It's the inflection point if you're taking calculus. It's essentially like the highest slope point of the graph. So if I have a weak diprotic base, that is the sample, and I'm titrating it with a strong acid. So what I would do first is for a weak diprotic base, I'm going to start not at 14 because it's weak. I'll start somewhere around like 12 or something. So I would kind of do something like this for the beginning. And then after that, what's happening is that I'm titrating it with the acid. So I actually have this kind of flat region for a while. That flat region is called the buffering region. It's called that because there's a buffer present. Okay, we'll talk about what the buffer is in just a second. And then it will go to an end point or an equivalence point, and then a second one like this. Oh, sorry, this is not good. Not good. Wait. That's better. I need to get very acidic because it is a strong acid that I'm using, so I want to be ending it very close to 0 on that. Okay, it's a little bit exaggerated around the equivalence points, but that's fine. So at this point, I have a buffer present that consists of the original weak base and its conjugate acid. So when the strong acid makes it in, it's reacting with that weak base to make the conjugate acid of that base. Now I've got a weak acid and base pair, which means I have a buffer. And a buffer keeps pH from changing very much. So during a buffering region, the pH is staying relatively constant. So I have a buffer right here. This right here is my equivalence point. It's the inflection point. It's the highest slope portion. So that would correspond to a pH here of around 9-ish. It's not an exact science. It doesn't matter where you end up with that. The big thing is being able to identify the attributes of this graph. And then here I have the second equivalence point. And the reason why I have to have 2 equivalence points is because it's a diprotic base. So it has 2 hydrogens that can be given. Okay. This is another buffering region right here. So I have another buffer present at this point. Okay, this has been on the last 2 diplomas. This is not a buffering region. The last one is not, because I no longer have a weak acid and its conjugate base present. I just have excess strong acid because the titration is complete, and I have the weak acid that's been made from the reaction with the weak base. I hope that makes sense. But this right here, not a buffering region. Yeah? Yes. The last diploma, like this. So actually, Alberta Ed used to not understand this, so I'm going to get a little bit heated. They used to think that was a buffering region. And they actually tested that way. And then they're like, oh, no, we got it right now. And then for the next 2 years, they tested on that fact. They actually had a question of label the buffering regions. There was 1, 2, and then one of the multiple choice options was 1, 2, 3. So they had 1, 2, and then 1, 2, 3. Anyways, yeah, not a buffering region right there. Okay. Titration to completion will be used for every proton being donated that can be. So that's what that terminology means. It doesn't actually mean much for you. It's just that the reaction completely happens. We're not looking at a weird equilibrium. When you're looking at titration stoic, you just do a normal science 10 level reaction and do the stoic. Okay, it'll say something like first endpoint, second endpoint. If it says first endpoint, only one hydrogen changes places. It says second endpoint, two hydrogens change places, etc. But you just kind of do this as a science 10 level reaction. So I'll give you an example. Let's say you have something like H2CO3, so carbonic acid, reacting with sodium hydroxide, NaOH. So sample, titrate. Okay. If it said first endpoints, what I would make for the first endpoint is one of these hydrogens would swap with the sodium. So I would end up with NaHCO3 nucleus and the water. Okay, so what happened here is one of these changed places. If instead it was second endpoint, then instead I would get Na2CO3 and two waters, which would change the balancing of the reactants, but you guys kind of get that. It's not crazy. So that means two hydrogens were lost from the carbonic acid in that case, not just one. Okay, if it's second endpoint. This is a reaction I'm looking at. Equivalence point versus endpoint. Equivalence point is theoretical. Endpoint is empirical. So for the endpoint, that has to do with an indicator. Okay, indicator changing color. Well, the equivalence point comes from kind of math or my titration pH graph of understanding that the inflection point, this point right here, that's the equivalence point. When you're picking an indicator for a titration, you want to get the equivalence point and the endpoint as close as possible. So you want an indicator that changes color, so it has an endpoint at the range of the equivalence point. So based on the information that I have here, right, my really roughly made graph, phenolphthalein would be a great choice for this for the first endpoint, because phenolphthalein is between 8.2 and 10.0 for a color change. So that would be between here and here. So phenolphthalein, awesome choice, right, based on how I do this. Okay, good. Yeah, this is the buffering region that I talked about. So here, buffering region, here and here, buffering region, not buffering region. That is not buffering region. No. Only occurs when acid or base is weak. That's another really important point. So if I had a hydrochloric acid and a sodium hydroxide titration, I don't have a buffering region because I don't have a buffer present. So buffering region is directly tied to the idea of what a buffer is, which is a weak acid and its conjugate base mixed together. If I don't have a weak acid and its conjugate base, then I don't have a buffering region because I don't have a buffer. So definition of a buffer is a solution, say mixture of a weak acid and its weak conjugate base. Both have to be weak. What does a buffer do? Resists change to pH. So keeps pH relatively constant, even when I'm adding acid or base to it. And the way it does that is if I add, let's say, acid to a buffer, the acid will react with the conjugate base of the buffer instead of increasing hydroxide concentration by reacting with water. So essentially it provides something for an acid or a base to react with instead of reacting with water when you add it. Okay, so which one of these solutions is a buffer? Is A a buffer? How come? HCl is strong. This is not a buffer. They are conjugates, but this is not a buffer, because this is strong. Is this a buffer? No, how come? Not conjugates. They differ by more than one proton. Is this a buffer?
They're both strong.
Yeah, like not even close. Well, this is weak, but that's strong, and then it's not conjugates. So this is like super far away. Ridiculous. Is that a buffer? Acylic acid and hydrogen oxide ion? Yes! Hooray, buffer. Okay, so two conditions, both are weak, and they're conjugate pairs. Differ by a proton. That's it. Hooray! Hi, equilibrium, good times. You ready for some organic?
Yes, sir.
Yeah, you are. Whoa.
Here on.
That's
We've
the
been on
end.
for 40 minutes. You guys fine? I want to drive through out in 5 minutes. That's why.
Why?
Why are you going to make lap? But that is way closer.
I feel like no matter how long the lineup is there, it takes longer for you to drive all the way there and get your stuff and drive back.
Because it's 10 minutes there and back. Like, in total. It's 2 minutes.
I just want to express again how wonderful it is that you guys came. I really actually just good for you. Thanks for get it? Dying it's step 2. The best. Okay, question often appears on the diploma of which one of these is organic? And I'll give you 4 options, or which one of these is not organic. So you need to know what makes up something that's organic and not organic. Now, I mean, carbon is important, yes?
Yes.
It's got to have carbon to be organic. But there are some carbony things that are not organic. And the carbony things that are not organic are carbon oxides. So what I mean by that is CO2, for example. Let's mix it up. Let's go with some blue. Yeah, it's crazy. CO2, not organic. What about CO? Not organic. Carbonates. So when I have a carbonate ion, like let's say CO3, so I have Na2CO3 or something like that, that is not organic. That's a big no. Cyanides, so CN, right? Something like lithium cyanide, LiCN, not organic. And carbides, this is when I have a metal matched with carbon, so carbon's acting as an anion. So something like magnesium carbide or tungsten carbide is not organic either.
So none of these are.
None of those are organic. These are all not organic. Okay, now what if I had something like this? Sodium acetase.
It's got to be. Yes, there's.
Is that organic?
There's.
It's got carbon, it's not on this list, therefore it's organic. So essentially, the tiny carbon anions are not organic in the oxides. So tiny anions. Cool. I don't want to go through a ton of this. We're not going to spend a bunch of time on the naming rules, because here's the dirty little secret. Although it's really tough to learn all of this for naming and stuff, it's not a big focus on the diploma. It really isn't. It's just that it takes a long time to learn. So find the longest parent chain Name the parent chain for branch positions. What numbers, sorry, not name. Yeah, anyways, there's rules. You should know them. It's been recent. But I have some examples on the next few pages that I think are worthwhile trying out a few. So here's 3. I want you to take 5 minutes, try them out, and see if you can identify what the name should be. Some of these are tricky, and this often does appear on the diploma. The whole thing of knowing branch versus parent chain. When you're picking your parent chain, what do you have to be careful of? Especially around like this one, for example. You pick the longest parent chain possible, okay? So always the game is try to find your longest chain of carbons. That's your parent chain. So I got 3 methyl branches here. I got to figure out numbering. If I go left to right, it reaches a branch on 3, same as right to left. The left to right has 2 3s. So left to right is correct. So I end up with 3, 3, 4, trimethyl hexane. So 3, 3, 4, trimethyl hexane. This one to the right is sneaky with its parent chain. Gotta go 1, 2, 3, 4, 5, 6, 7, 8. In other words, I have an ethyl branch and I have a methyl branch. Ethyl comes before methyl because it's alphabetically first. So in the name, I would name this 5-ethyl, 3-methyl octane. So 5-ethyl, 3-methyl octane is the right name there. The reason why I go the numbering I do, getting to 3 here, is because that gets to a branch first. Even though it's not the ethyl branch, it's still the first branch I can get to in the parent chain. All right, now this line diagram. 1, 2, 3, 1, 2, 3, but I have 2 of them on 3 here, so this is going to be the better way to go about it. So I have this branch, so 2 ethyls, 3 ethyls, and then a methyl here. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I've got 3, 3, 7 triethyl. 8-methyl decane. Okay, now these are all what type of hydrocarbons? Alkanes. Are they saturated or unsaturated?
Saturated,
Awesome. If I put bromine with these, what would happen?
unsaturated. Wait, no.
Describe to me what bromine would do with this. So I put bromine in, it's orange. What happens? It stays orange. There's going to be a bromine test question. So I can bring these up.
I thought we were like adding bromine on these, I was like,
Yeah, so if it was unsaturated, it would add by addition. Instead, it's going to be substitution. Okay, saturated versus unsaturated. Alkenes are unsaturated. Alkynes are unsaturated. Cyclos, if it's an alkane, it's saturated. So even though for a cycloalkane, the formula is CnH2n, in other words, I've lost 2 hydrogen by closing the shape, right? So I got to take away 2 hydrogen to make it close shape out of carbons. So I lost 2 hydrogens, but that still is considered saturated. So when you think about saturated and unsaturated, unsaturated means I have a carbon-carbon double or triple bond. Yeah. Benzene we don't like talking about because it's aromatic. So technically it is kind of unsaturated, but those double bonds aren't normal double bonds because of the resonance. So because of that, they don't act like a normal double bond by doing addition reactions. They do substitution instead. So we only typically talk about this for aromatics, not aromatics. Okay, so how to test for saturated versus unsaturated? We use the bromine test. Saturated stays orange for longer. And that's because substitution is slow. So saturated stays orange for a long time because substitution is slow. It takes ultraviolet light to occur. So it's not an instant reaction. But unsaturated, orange fades quickly. And this is because addition is fast. Maybe this should be said to give context. Bromine is orange. That's why this happens. Kind of a basic fact there. So the reason why the orange fades or goes away is because the bromine has now reacted to make a halogenated hydrocarbon, an organic halide. So now I no longer have the bromine as Br2 liquid. It's now added to the organic compounds. All right, 3 more that are a little bit of twists on alkanes for you to name. We'll try those out, and then I think we're kind of past the naming stuff. Why don't you give those a quick try and see how it goes? pathways and I name the cyclobutane. I'll have 1 and 2 on the branches. So which branch is the lower one? Yeah, right. Ethyl comes first alphabetically, so it's going to go 1, 2, 3, 4. The parent chain is only the cyclo. The rest are considered branches. So I have an ethyl and a methyl. So I have 1 ethyl, 2 methyl, cyclobutane. Okay. Top right, I have an alkene here because I have a double bond. So I got the alkene right here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. The alkene is priority, getting to that double bond first over branches, so I have to make sure to get to that as quickly as I can. So I have 3, 6, 7. Trimethyl. Ox. 2-ene. So the number before the E is the first carbon that participates in the double or triple bond, right? So 2-ene. Okay, now when I get to the cycloalkyne, 1 and 2 both have to actually be on the triple bond. Okay, so now I have to figure out, is there to go 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6. It's obviously better to go 1, 2, 3, 4, like this. Okay, because I get to the branches quicker that way. So I'm going clockwise around. So what I have then is 3, 4 ethyl, because here I have an ethyl branch. So 3, 4 ethyl, cyclo, hex. You could put 1 I, or you could leave it off, right? You can leave it off because of the fact that, oh, die, thank you, yes, Oh, that did. Eraser when you need it. Diethyl cyclohex 1-ine, or you could leave that 1 out of it because obviously it has to be on carbon number 1. I don't have another option for priority. Okay, isomer. There were several questions on your organic test that had to do with isomers, and you picking up 2 isomers, right? They were actually kind of poorly done. Like there were 4 structures, one looked like this. Yeah, and then you had to figure out what the isomers were of the options. What is an isomer? Nice. Same formula, different structure. So same formula, in other words, same atoms. Different structure, which means different properties. It's a different thing. Okay. We can get really complex on the diploma, and this is something they focus on if you're dealing with the alkenes or isomers or not. How do I come up with a formula for this quickly? This has 1, 2, 3, 4, 5, 6 carbons. C6. How many hydrogens will it have? 2. Oh. I'm always starting with alkane of 2n plus 2. So 6 times 2 is 12, plus 2 is 14. I subtract 2 for every double bond. I subtract 2 for every cyclo. And I subtract 4 for every triple bond. That's what the next slide is. This is an amazing way to figure out these questions really quickly. The diploma has, I talked about this during organic, often these really complex names or structures. and they want to know what the formula is for those complex names or structures. The easiest way to do this is to use these tricks, to realize how many hydrogens I take off for each kind of thing I could have in the structure. So for a double bond, again, it's 2, triple 4, cyclo 2, and we're always starting with CnH2n plus 2. So the next one is a great example. I love this. We don't even have to draw this. We don't. We can figure it out from the name. Methyl. Okay, so sorry, ethyl first. How many carbons is that? 2. Methyl. 1. Hence? 5. So I have 8 carbons. Okay? I'm starting with 18 hydrogens. 2n plus 2. 8 times 2 is 16, plus 2 is 18. So I'm starting with 18 hydrogens. I'll just write that down. Now let's go back to our name and subtract jump based on what we have. What will cyclo do? Cyclo, I lose 2. Ene, I lose 2. Easy. C8, H14, I'm done. It's over. I don't have to draw it. I don't have to worry about all the hydrogens. I can just figure it out from the name. Do you want to do another one like that?
Yes.
Could be amazing. Yeah, let's do that. Let's do 2,4 diethyl cyclo Got to make sure this actually will work as a structure. Cyclo hept 1, 3 diene. Wow. Whoa. It's crazy. Do a minute. Figure it out already? Sweet. Two, 4 diethyl, how many carbons? 4, yes. 2 times 2 is 4. Cyclohepts, 7. 1, 3 diene, don't care about that right now. I got 11 carbons. How many hydrogens am I starting with then? 24. So I'm starting with 24 H's. Now let's make my subtractions. Cyclo minus 2, right? Diene minus 4, because I have 2 minus 2's. So I take away 6 from this, it's C11H18.
Can you make it a really good number?
Probably not. I don't know. Not like having a correct name. I'd have to draw the structure first, then name it, and then get to this. You don't want that. This is true. It's fun, right? It's fun because it's neat that we can just figure this out.
Yeah.
In this kind of cheating way without drawing it. But yeah, it's a whole idea. Okay, aromatics. Important to realize that benzene is special. Benzene is the only aromatic you have to know about. Benzene is C6H6. And the reason why it's special is because it has something called resonance. In other words, you can draw benzene in two different ways in terms of where the double bonds are. So keeping these carbons the same carbons, I can move the double bonds from here to here, and then here to here, and then here to here. These double bonds actually don't exist in a specific location, but they're delocalized and they're kind of actually belonging to all these carbons. This is not double bond in length or strength. It's actually somewhere in between a single and a double bond. And as a result, it doesn't have the same reactivity that we would expect from a normal double bond, which means benzene does not actually react by addition, but reacts instead by substitution. And so even though it's got double bonds, it's not normal double bonds. So what should you know for the diploma? Keyword of resonance. Resonance. And the fact that these are not normal double bonds because of the delocalization of electrons, they're special. Special. We can draw benzene like this, or we draw it often like this. And the reason why it has that circle in the middle is that's meant to represent the fact that these electrons are delocalized and kind of belongs to all of the carbons. Benzene is like a little bit communist. Yeah, there's a lot of sharing going on. All carbons are equal. This caused some confusion in the past, and I realize that. If I have a benzene in the middle of a hydrocarbon, I have to name the benzene as a branch. So this is now called a phenyl. P-H-E-N-Y-L. And the reason why is because it's attached to a middle carbon of a hydrocarbon chain. So I don't think this is worth spending a lot of our time on, but this would be called 3-phenyl hexane. It's 1, 2, 3, 4, 5, 6. Oh, this could be fun. How about this? What's the formula for that sucker? Huh? C12. And the cycle. So I'm subtracting 8. So it would have been 26. Now it's 18. Okay, cool. Next one, is that an aromatic? No. Okay. There's no triple. Yeah, there's no double bonds, there's no benzene and stuff going on. I would need to have the 3 double bonds, 1, 2, 3, in order for it to be a benzene. This is simply a cyclohexane. So this would be 1, 2, 3, trimethyl, cyclohexane. What's the formula for this? Oh. C9. Yeah. Start at 20, right? 9 times 2 plus 2 is 20. Minus 2 for the cycle. C9. All right. This feels like a big chunk, but it's okay. Let's skip entirely in this presentation. No, the functional groups come after this. That's fine. Fractional distillation, and I know that we did this closer to the end. There's always one question on the diploma on fractional distillation. Always, always, always. Guaranteed. So how this works is there is kind of heat at the bottom, fire, furnace, whatever, okay, that's heating this up. It's hotter down here, it's cooler down here. If the thing that's at the level boils, so the temperature at that level is higher than the boiling point of the compound boils to the next level. It goes past these bubble caps, and it makes it to the second level where it's a little bit cooler. If it still boils at that temperature, it goes up to the next level, and the next, and the next, until it reaches a level where it goes through condensation and now lives and stays at the bottom, because the temperature there is lower than its boiling point. So this works on boiling points. This is hotter down here, and as a result, I get larger hydrocarbons at the bottom. So stuff that's longer, higher molecular mass ends up at the bottom. The primary reason for this is London dispersion forces you learned about in Chem 20. The bigger the molecule, the stronger the LDF. At the top, it's cooler. And this is where I have the smaller hydrocarbons. Smaller stuff goes to the bottom, or top, sorry. And that's because it's boiled all the way to the top. Do I need to explain that more, or are we solid about it? If you know those two facts, you're just like you're set, you're fine. Solvent extraction, there could be some questions of, does this dissolve in this or whatever? So solvent extraction is a way to separate out something you want from a mixture, but the fact that some things are more soluble than other things. The big thing to focus on for this is hydrogen bonding in small size. So for example, CH3OH dissolves really well in water. So it would dissolve in water. And the reason why is if I take a look at the structure for CH3OH, it has hydrogen bonding because of this OH bonds. So H is connected to F, O, or N, and the main one you're concerned about is the O, with the types of compounds you learned about. Then it will dissolve in water. Also, the smaller the size, the more easily it will dissolve in water. Essentially, with solvent extraction, like dissolves like. So things that are more similar to it for intermolecular bonds and forces, it will dissolve better in those layers. So a great example, let's say that I want to get out, I made some structure, okay? Let's say I made some cyclopentene somehow. Let's make it a methyl cyclopentene. I want to get this away from the rest of stuff that I have in the mixture. I want to isolate this product. What I would do is I would actually add something like hexanes to this. Okay, so I would add hexanes. 6. And the hexanes would dissolve this. So now I could actually evaporate off the hexanes or evaporate off this, and then I've got my pure product. Hexanes dissolve this because both of them are non-polar, and there's no hydrogen bonding. I feel like I lost it.
You want to back up like
No hydrogen bonding. Okay. No OH for both of these. Same. Dissolves. Isomers?
No.
No. Not isomers. Just, I could use this as a solvent to dissolve this. Now let's say that this was mixed in with something like this. Right? So these were a mixture together somehow. This would dissolve this, but it would not dissolve this. Do we see why? This has a strong bend.
non-polar?
Yeah, then
Yeah, polar dissolves polar, non-polar dissolves non-polar. Chem 30 though focuses the most, Alberta Ed, on the hydrogen bonding, which is interesting. That's for them the distinguishing feature. It's a little more complex. But yeah. Okay, so solvent extraction, just think about the intramolecular forces, specifically though hydrogen bonding. And whatever has hydrogen bonding will dissolve in other stuff with hydrogen bonding like water, and whatever doesn't won't. There could be a question like this where I have, let's say, 2 carboxylic acids. I think I had something like this on a worksheet or your workbook, I can't remember. Which one will dissolve better in water?
Not the top.
The top one? This one dissolves better in water. Smaller. So think about this part of the molecule. You see how this doesn't have the hydrogen bonding, it's a non-polar part? That part will not dissolve well. So this will be better at dissolving in water than this one. Because of the smaller size and the fact that it doesn't have that non-polar tail. Hopefully that makes some sense. Combustion, complete and incomplete. I don't want to get into this a ton, but complete makes CO2 because I have enough oxygen. So I have lots of O2, lots of oxygen going in. So it makes CO2 gas. Incomplete combustion, I have less O2. So this will make CO or carbon. So because there isn't enough oxygen present, the combustion will not make the CO2. It will be actually less exothermic, it doesn't release as much energy, and instead it's going to release carbon monoxide or solid carbon. This is obviously not something that's typically desirable, right? If your furnace does this and it's making carbon monoxide, that can kill you. So that's why it's really important to make sure that enough oxygen is going into the intake of your furnace or anything that's actually doing combustion like a heater. This hasn't come up on the diploma for a while. I feel like it's due. I feel like, given that it hasn't shown up in like the last couple of years, there's going to be something about incomplete combustion on there. I could be wrong, but that's my prediction. Functional groups. Functional groups are called functional groups because they do something. They essentially are like places where reactions or stuff will happen to the compounds. So they somewhat define the properties of that class of compounds. So I have the class of molecule, and then I have the name of the functional group. It's not the same. So alcohols have a hydroxyl group. Think hydroxide, hydroxyl, right? OH on it. Carboxylic acids have a carboxyl. Here's my ester. You'll have questions, and I talked about this in the past, where you'll have these really complex molecules, and we'll ask, hey, what functional groups do you have on this complex molecule? And you have to essentially figure it out. Also important to know that a carboxyl is made of both a carbonyl and a hydroxyl. Put that together, I get carboxyl. So carbonyl, C double bond O, and hydroxyl. So I'm going to see if so this is naming. I wanted to show you an example, so I'll draw it on the board right now, of something where you are going to tell me what functional groups it has. I did a few of this earlier during organic, but on the exam, there was a question like this that actually didn't end up very well done. So I think it's good to address. What functional groups does this have? Hydroxyl? Yep.
Hey, don't laugh at me, I was right.
There's the hydroxyl. What else was that?
Carbox. No. All right. There's no H on
There's no H on that one.
Benzene.
Nope. Not a benzene.
What's that? Is that an ester? Is that a cycloester?
Yeah, I guess.
Actually.
Yeah. This is an ester. It is not a carboxylic acid because there's no H on this O. This is probably safe. Okay, why don't you try to name these really quick and see how that goes. here are the names. 1,4-dibromo-2-ethylbenzene, 1,4-4-ethyl-3-iodo-2-propyl-cyclobenzene. 3,5, forgot the dye. Gotta get it together, right? Jeez. 3,5-diethyl 6-methyl octafluorol. Then I got 3,4-dimethyl hexanoic acid.
That's like
That was weird, eh? Yeah, so many different groups. Are halogens a branch? No, they're a functional group. We name them as a branch. It means that like we include it in the name as if it's a branch, but it actually is a function. Yeah.
This is
Here I have an ester. You gotta recognize the alcohol portion and the carboxylic acid portion of the ester. My alcohol portion is right here, because it's the one that does not have the carbonyl group. So it doesn't have the C double bond O. And then here's my carboxylic acid portion. Now, when I say that, I'm just talking about the naming. It's now an ester. It's not two different things, but it was made for two different things. So this is called the methyl. That's the alcohol portion. Full on space, propanoate. So esters have that O8 ending. So methyl propanoate. Next, I've got a carboxylic acid, so I have a carboxyl group. That is going to be carbon number 1, just like with the ester. Okay, wherever the ester functional group is, that's my 1. 1, 1, 1. Or sorry, this is 1 for the alcohol portion, 1 for the carboxylic acid portion, 2, 3. Here I have 1, 2, 3, 4, 5. I actually have 3 methyl groups on this. So I have 3, 3, 4. Trimethyl. Hence, enoic acid. And I have a break, I have a space between the oic and the acid. Now this would be multiple choice, right? That's the beauty of this, and that's where you don't have to know it as well as some other stuff, is that because it's multiple choice, you just have to be able to distinguish what the right answer is. Okay, reactions. Reactions are a hard thing to teach quickly. I highly suggest that you go back to your reaction worksheets and try them out again. Give them a go, see how it is. Because they're not easy. You need to have these a bit straight in your minds. Addition and substitution are huge in their differences, like in terms of knowing them. It's the most popular two that you'll see the most. Addition happens to unsaturated aliphatics, not aromatics. Well, substitution happens to saturated aliphatics or aromatics. So in addition, I'm adding to a double or a triple bond. In substitution, I'm swapping out a hydrogen for another atom. And then I have elimination as well, making a double or a triple bond, and esterification comes up a ton. Combustion, I think, is going to come up this year. I'm going to skip ahead, read through this, take a look at it. I think I've got, a few reactions here. And then we got polymers, graphene, and red. So I think it's worthwhile, and I said I was going to have you here till 2, and we have 25 minutes left still. So I know it seems like it's been a long day, but let's power through.
4 hours.
4 hours, glorious, 4 glorious hours. Why don't you try out? What? You tell me. How do you want to do this? You want to do it slide by slide?
Sure.
Okay. 5 minutes for each one?
Sure.
Perfect. Try out this slide. See if you can predict the products. Okay. Remember that sometimes I get isomers. Make sure you predict all the products.
No, it wasn't. We were talking
One of the fish just escaped.
It sounded.
Is the fish dead?
I don't know.
Did the fish just jump out of water?
Did it actually leave the water?
Sounded
Or
like
the tank?
we didn't hear like it's trying to fly.
There's water all over.
John would be in it. He's so sick of Chem, he just drove him.
Fish just starts committing suicide.
Oh yeah, by the way, I was this fish.
He's looking for the fish.
I finally found the fish. I was like,
If one of Benzene's fish dies during their exam, we all pass. If one of your fish dies during the exam, we all pass.
Sorry?
If one of your fish dies during the exam, we all automatically pass.
I don't think that's how it works. If one of you dies, I think you
that's a traumatic experience.
Yeah, it is. Imagine writing your exam and halfway through a fish just jumps on your exam. No, it jumps onto your exam. He's like, no, I got this one.
I've been
Your paper's all wet. I don't think I'd be able to write an exam. I'm so
No, I believe if you manage to vomit on your exam,
Really?
You get
I don't know if you don't have to take it or you get to retake it.
So if you don't have to take it, so you can put yourself through, if that's your final mark, is your class then?
Those are good questions.
If you know the answer, I wouldn't be complaining.
Like, do they just,
By Monday.
do they just like,
So that's it.
I guess they just like assume that if one person knows what you got in class is what you would get on the exam.
I think that's how it works. There's a 1 year during the where people didn't have to take it.
Oh, yeah.
Because it's funny.
Oh, I didn't hear that during like one.
Yeah, during
Wasn't that on the app?
no, so you're two
So if I was really good.
So, if what's you know like how there's like those drugs that like basically kill you but don't actually kill you? Is that actually a
It's
thing?
like 6 hours of like Juliet. Juliet.
I don't know what you're talking about. Oh, like you go into like a school.
Yeah, but like it's only for like 3 days or something like that. Where you're still alive.
I mean, people get put into a medical coma, right? But I think it's very much like, it's not like one pill and you're good. I think it's a thing of continually keeping levels in this way.
Isn't it give you something like that?
Or you can just do all the tests. You can just take
I
your
feel
good
like
stuff
I've
right
read
now.
this.
I think I'm gonna.
And you know what?
I think I'm gonna.
So let's say it just goes completely wrong.
And
It's fine. I don't need
Exam again after summer school. Like they have you can actually take the exam again in like a month or something.
Oh, if I get to wait to finish the diploma.
Yeah, I think they actually have another diploma that takes place at the end of July or beginning of August. Or
yeah,
something.
that's when I selected
Literally.
Oh, right, sorry, I think this is the end of the year. And
That'd be nice.
for April.
Because if I hypothetically was writing this in June,
Yeah.
I couldn't take it. I thought I'd have to wait till transfer.
No, yeah, we'll have to wait till September or beginning of August. My exam was like August. Yeah. Nice.
Yeah, I thought you were writing the same time.
Everything is fixed, you know? Things go poorly, so what? You just fix it.
If you hypothetically gone
Yeah, that's my goal. They had tests.
and you have to.
Why did you die?
Because I know for a fact if I'm sitting here and I get it from work, I know someone who is.
so propanol would look like this for the structure. So what would happen here is that this is going to be an elimination. I don't know what else you could try to possibly do for this. The H2SO4 is a catalyst for elimination. So what would happen is this OH and a neighboring hydrogen would leave to make a double bond. So what you'd actually get is CH3, CH, double bond, CH2, and you would get a water. So propene, water are my two products here. And again, this is an elimination. Okay, next one, I've got butene and hydrogen. So I'm adding this to the butanene. Platinum or palladium are typically catalysts for hydrogenation, but this is just an addition. So all I'm doing is I'm adding EH2 to these two carbons here that were double bonded. So I'm breaking the double bond in order to add the hydrogens. So I'm taking an unsaturated hydrocarbon and making it saturated, and I get CH3, CH2, CH2, CH3. It's the only product, so I'm getting butane. So again, that's an addition, and specifically, it's hydrogenation. Okay. So it should be relatively quick. Got a few more slides here. I'll give you a few minutes to just try out. Why don't you try out all four? Okay, let's do this in one round. Try out all four of the next reactions. We'll take them up. And then we got a few quick things about polymers, and we're done. We're cracking petroleum reactions. We're almost there. Like not actually cleaning up. But
Hunter. Oh, I think mine is like so I need to find
that's what we got.
Oh, no. So, because we have the exact same market bio, and she only said back in the
well, I would like higher, but I'm just calculating hypothetically what's the worst I can do.
Now, I don't want to throw a wrench into this, but is it possible with performance-based stuff to go secondary that will not this?
What?
So post-secondary is now going to performance-based.
Yeah. No, but I've already applied and done all this just conditional. I revised.
Just because a lot of this is new, I'm not sure if it'll stick to everything.
So basically what you're saying, I'm not.
No, what I'm saying is that they probably will get more selective in terms of the marks they take because they want guaranteed success of people who get in.
They don't want people to
Because their funding depends on their success rates.
yeah, but there's people out there who Same. Same thing.
Okay, so I actually have 3 products for this one. I can have 2 isomers because this bromine can replace 2 different types of hydrogen. All of these ones are equivalent, they're the same. Okay, but this one in the middle is different. So what I end up with is 1 bromo, 2 methyl propane. I have 2 bromo, 2 methyl propane, and then I have hydrogen bromide. Sorry, I know this is a mess. Okay, butynoic acid and ethanol. This is going to be an esterification type of reaction. Why don't we do that on the board here? So you build up over there. So when you do esterification, I think the best way to go about it is actually to draw a line between this O right here and the carbon that the OH was attached to on the alcohol, and that's now how it's going to be connected, and then redraw it based on that new connection. So I've got CH3 to CH2 to CH2 to CO, and then O, and then now I'm connecting to this carbon. So I've got CH2, then I have CH3. And this is ethyl butanoate. And then the thing that's really easy to forget is the water as well. I need to make sure I have the water that is the byproduct of esterification on top of that. This one often is actually very poorly done, but it should be the easiest one. 2,3-dimethyl pentane and oxygen. What am I going to get? Oxygen, CO2 and H2O. As long as it's complete. So CH3, CH, CH3, CH, CH3, CH2, CH3, plus O2, double bond between the 2 O's, making CO2 and H2O. Easy peasy. Okay. Chlorine and methyl benzene. Oh, this one is awful. Actually, absolutely horrible. And you'll see why. There's so many isomers I can make. Chlorine. And methyl benzene. This is a substitution, and the chlorine can replace any one of these hydrogens. This one, which is the same as this one, which is the same as this one, and this one. So I actually end up with 4 different isomers I can make. I'm going to draw the line diagrams because I'm lazy. So I can get this, where the chlorine is on that top methyl. I can get this, where it's replacing this hydrogen. get this one. And in that para kind of spot too. It's unfortunate how I do that. Let's do it this side. It's the same. And then finally, I also will have HCl as a product, little byproducts there. This one would have a weird name. Because I have to name it as a phenol.
Isn't that?
So it'd be like one, I'll just chlorophenol. This would be, what would I have this? I would have this 1-chloro-2-methylbenzene. This would be 1-chloro-3-methylbenzene. I would have 1-chloro-4-methylbenzene, and then of course hydrogen chloride. Okay, anyways, got the structures there, we'll move on. Naming is kind of probably redundant at this point. Polymers, most polymers are made from an ethene variant. So ethene being CH2 double bonded to another CH2. Most polymers are made by addition by this as kind of its backbone. There can be other stuff on there, but it's going to have a double bond between two carbons. In order to come up with a polymer name, I just take the name of the monomer and add a poly to the front. So for example, this is vinyl chloride. Vinyl is actually another name for ethene. So now I have polyvinyl chloride. The way that you would name this and the diploma would talk about it would actually be polychloroethene. Okay, so poly and then chloro on an ethene group. So polychloroethene would be the right name. If I had this as a monomer, CH2 to CH to CH3, that would make polypropene. If you heard of polypropylene, like banks, or banks, that's actually, this is the building block. So what that actually makes for a polymer is you have C to C to C to C to C to C. Every second one of these would have a CH3 coming off of it. It's like that. And the reason why is because this CH3 ends up down here, and that kind of repeats over and over and over again for the backbone, that ethene, two carbons bonds together by addition and ends up kind of like that. Hopefully you see that or that makes sense. I feel like I'm not explaining it fantastically well, but you get that for a long time. So that is an example. So basically just add poly to it, and you're essentially good for the polymer name. Esterification can make polymers as well, resulting in a polyester. This is a type of condensation polymerization, which means I get a small molecule byproduct. In the case of esters, that's water. But it could be hydrogen chloride or ammonia or anything else that's just an extra product. Yeah. This just says repeat it over and over and over to some arbitrary number. Could be a million. Just, this is the repeating unit. But it's all connected together in a row. Yeah, so polyesters, in order to make them, I need to make sure that I have on my monomers I start with carboxyl groups on both ends and hydroxyl groups on both ends. So I have two monomers that make this, but that allows a polymer, or a esterification reaction to happen at both ends. Okay, so it can continue over and over and over again. Anyways, if hearing this, you're kind of like, oh, I don't remember much about polymers. Hey, look it up, right? Do a little bit of reading in your textbook, your notes, or whatever. It's not actually that tough. It seems tough, but it's not that. It really isn't. You don't have to like come up with these monomers, by the way, right? But you should know that it's an esterification type of reaction that's happening here, and that's a condensation type versus when I have the ethene, so a kind of unsaturated addition polymer, That's an addition type of reaction. I don't know if I said addition anywhere here. That may be right in. This is an addition polymerization reaction. In contrast to the condensation that happens with the polyesters. Okay, last slide is on these different types of hydrocarbon reactions, which occasionally show up in very little detail. Cracking is exactly what it sounds like. I'm breaking it apart. It's essentially a type of elimination. Okay, I'm just breaking it into smaller pieces. Normally, there isn't a distinction between catalytic cracking and hydrocracking, but hydrocracking just means it's making saturated stuff. Okay? Well, catalytic cracking is making something that's unsaturated and saturated as well. You get some double bonds in there. Reforming, think about it as the word of reforming if you're making something fancier. Something like you're making benzene, okay? Or you're turning smaller things into larger things. You're just making it fancier. So reforming, making it fancier. And then alkylation, also known as isomerization, means you're taking something that, and sometimes these are actually treated as the same. Okay, they kind of use these terms interchangeably. But what you're doing is you're taking something that's a long, continuous chain like this, and instead you're making it so it's kind of branched like this. Okay, so you're just moving it around to get more branches. Why do we do this? It actually makes better fuel. And to maybe have more branches or something. So it's in order to get it to have the branch or the structure that we need for its purpose. Any questions about these at all? Just to maybe feel confident about this, because I know in class it seemed like this was really quick for this stuff, right? Read a little bit of it in your textbook. It's not actually that much more detail, but it's good to read that to get a little bit of background on these types of reactions. That's it. That's the review for all of them. Crash course on Monday. Okay. Highly recommend that one. It's the major points of what I expect to be on the diploma. I think that's the best one out of all of them. So hope to see you then at 3. It's gonna be great.
3 to 5, right?
3 to 5. Thanks for coming. Hopefully you found this useful. If not, I'm sorry.
It was good, thank you.
Okay.
Thank you.
Yep, sounds great. Let's stop that.